So a couple of things, as I said in yesterday's office hours, if you are able to solve problem 1 and problem 2, problem without excluding challenge problems, then you are in a good state now. And I will introduce you more ideas in today's class, and they'll help you solve the rest of the problems. So with respect to data types, and we have looked at only one data type, which is the integer data type. When we declare a variable, as saying int a or something like that, indicating that the variable holds values which are of type integers. And integer variables are allocated 4 bytes of memory. And and then in the homework problem, so there are a couple of places where you will not just be able to solve the problems using integer variables. Like, for example, when you want to find, there is one problem in which you have to find, I think problem number 4, you have to find sigma I is equal to 1 to 1 to n square root of I. So this is one problem. So like square root is square root of an integer. It need not be an integer. So we need to introduce new data types. So the new data type that is introduced, that is required, is what is called as a float, using which we can represent real numbers. Okay, not all real numbers, no. So what happened? Yeah. So we have today, in today's class, we will look at this new data type called as float. As we are on data types, there is this nice question from Nipun that he is using integers, but no, all the values beyond some range, he is not able to capture them. So we will talk about it in a different class, but in today's class, I will just point you to the fact that since we are using only 32 bits, only 4 bytes is 32 bits, right? So for int, we are using 32 bits. So 4 bytes is 32 bits, and we use a particular representation format. And using that representation format, we can represent all values which fall in this range. Okay, all values which fall in this range we can represent. So why is it this? We will we'll look at in a different class. We'll look at it in a different class. But are you with me? So if the values that you are working on, if they don't fall in this range, then you may want to go to long integer. So long integer in some systems, depending upon the system, it can be 4 bytes or 8 bytes. And so you may want to, again, as per the application, if in your application, if you are representing integers which doesn't fall in this range, you may want to try using long integers. And sometimes your data doesn't even fit into 8 bytes, then you have to work more harder. In fact, in many cryptographic or almost or all cryptographic applications, they work with 128 bits, 256 bits, 512 bits, etc. So the default data types provided by you for C programming language is not sufficient to do arithmetic that is required in cryptographic applications. So in those cases, you need to write your own library for storing integers and performing arithmetic on integers. But again, we will revisit all these ideas later. But all I want you to get from this class is, because since we are using only 4 bytes for integers, this is a range of values that we can represent. Are you with me till this point? Okay, right? Yeah. And then, yeah, let's keep going. So and then you have to use floating point numbers. You have to use floating point numbers. There are, whenever you have numbers like 1.2 or 10 power minus 6, some decimal numbers, fractional numbers, then you have to use floating point or double float or double precision numbers. We have 2 precisions here. One is called as a single precision floating point number, and other is a double precision floating point number. So double precision, it uses 8 bytes to represent your number, so it can represent a longer range, bigger range of numbers. And floating point numbers, they float. If you declare a variable as float, then 4 bytes are allocated to it, 32 bits. So the actual representation, how these integers are represented, how floating point numbers are represented, you will perhaps learn in digital DSM course. But in this programming course also, at some point, we will see the underlying representation of numbers. Okay, but not today. So today we will take the easy path. Whenever you want to work with fractional numbers, declare a variable as float. So that is the story. And one point we need to, yeah, so let's, and then, so there is what is called as a typecasting. So when, like for example, when you want to add an integer to a floating point number, so let's first, before we get there, so let's take a simple, let's write some small code. Single precision, for the time being, no, you just take single precision means it can represent some range and it represents some granularity. Double precision means that it has a bigger rate, can represent a bigger range of numbers, and the granularity, the difference space between 2 numbers, is smaller, much smaller. So we will revisit this, but you just, for the time being, just use float or double. It should be all right for the problems that you work now. And yeah, so now let's go to new file. Okay, so now let's, if you want to read a floating point number, so for, let's say, so this is let's say you want to find the area of a circle. So we define 2 variables, float, area, and radius. And so we have this statement, printf. Maybe we can even have circumference. Okay, so printf enter the radius. And then if you want to read a floating point number, the format specifier that we have to use is %f, scanf, and we want to read the radius. Are you with me here? So in order to read a floating point number, we have to use the format specifier %f. And then we compute area is equal to, so 3.14 times. So I will introduce one more idea, which is called as a constant, so preprocessor macro. So let's say we say hash define. Remember, whenever we have this hash symbol, then that statement is processed by C preprocessor. So what the C preprocessor does is, before the program is compiled, wherever pi is present, it replaces pi with 3.14. Okay, so area of, so radius times radius. And then circumference is equal to 2 times, pi times radius. Does this make sense? Are you all with me? So, and then we will say area is equal to circle, we'll just say circle radius. And the format specifier for printing is also %f. Circle radius %f, area %f, radius is also. So remember, so we have radius, area, sorry, the last one should be circumference. Good. So in this program, so there are multiple ideas, new ideas we have introduced. So pay attention. The first idea is this notion of pi. We used this macro constant. This is a macro constant. Okay, there is one small error. Yeah. So pi is what is called as a macro constant. What it does is, what C preprocessor does is, wherever pi is present, it replaces it with 3.14. Because let's say you have written a large program, with some 10,000 lines of code, and the program is not present in one file, it is present in some 100 files. And so you use initially the value of pi as 3.14. And later you feel, no, that's not a good approximation. You want to use a different approximation for pi. Then changing it all over the place is a painful thing. Or you and your friend are working together on a project. He is using one approximation for pi and you are using another approximation for pi. And that can lead to bugs in the program. So in order to resolve this, you can just define, use this pi. Is defined constant. No memory is allocated. On line number 3, because of the defined statement, there is no memory that is allocated. Okay, so in fact, if you want to see, let's go and see what happens. Let's go to the terminal. We can use a variable for pi also, but this is a much cleaner way to do it. Variable you can modify. But the constant capital Pi, it is not a variable. So now let's see CD CP21A. So I will now pay attention. Please pay attention to what I'm saying, and then I'll take your questions. So if you do CPP, this is not, I'm just invoking the C preprocessor. So let me generate a float.i. So what the C preprocessor does is it takes a file float.c and it generates an output which is consumed by the actual program, which is consumed by the actual compiler. And if we see, you should be patient. Listen to me first and then ask your questions. So you can see this is the transformed program. In the transformed program, you don't see capital PI. Wherever PI is there, it is replaced with 3.14. 3.14. Are you with me here? So capital PI, it's not a variable. It's no, it gets replaced even before the actual GCC compiler. It wouldn't even look at capital PI, and that PI gets replaced with 3.14. So we just use this. We don't need to do it. We don't. So there are some other things going on. I don't want you to pay attention to it. All I want you to understand here is when you give this command gcc float.c, what GCC does first is, GCC is a kind of, it invokes multiple programs. The first program, so what happens is this is float.c. This program goes to a program called as CPP. This is C preprocessor, and it generates another program called as float.i, which goes to a compiler, actual C compiler called as CC1, and then it goes on like this. What your GCC does is it invokes this chain of small programs which process your source code file. Oh, writing is not visible. Same problem. Just give me 1 minute, please. How about now? Can you see now? Yeah. So your float, the float.c is passed to CPP and float.i gets generated, which, so float.i is processed in some way and it is passed to CC1, which is the actual compiler which translates your C program into assembly code. And GCC does all this for you. It calls CPP followed by CC1 followed by assembler, linker, so on and so forth. And what we have just seen right now by issuing the CPP command, okay, so we issued a CPP command here, is try to observe the intermediate file that got generated because of by using CPP. And now let's go back, and this is float.i. You can see, wherever capital PI is there, it got replaced by 3.14. Are you all good here? This one, this point. Nice. So if this is good, then let's go back to the thing. What's the advantage of pi? So if you just, your friend, your whole project will use pi. Later on, if you want to use a different approximation for pi, you just change on line number 3, automatically it gets changed everywhere. As simple as that. And on line number 7, we have declared 3 variables which are of type float. They can hold fractional numbers, 10.7, 8.7, whatever they are. And we use a scanf %f format on line 11 when we are reading floating point numbers. And on line number 13, we said area is equal to pi. There is a multiplication operation that is happening. And multiplication operation is what is called as a left associative operation. So multiplication, it is left associative. Left associative. What it means is, we keep writing this expression tree. So area is equal to So pi times radius times radius. So what happens is this part gets first multiplied because this and this gets multiplied, and whatever is the result, you multiply it with the operand that is on the right side. And so you multiply this, so this is left associative operation. You are multiplying from the left. And then whatever the result, let's say if radius is equal to 2.0, this is 3.14. So what you get is 6.28, 6.28 into 2.0, whatever is it, it gets assigned to area. Are you with me here? Now, the second thing, circumference, I use capital C to just make my life easy. If we write the expression tree, I want all of you know, anyone who has a doubt, please ask me. So 2 times pi times radius 2 pi r. So here, if you see this thing, no, C is the circumference. I'm using shorthand. So in when you are mathematically speaking, 2 times 3.14, it's not a big deal. You know, it's perfectly fine. But from a computer perspective, 2 times 2 is an integer and pi is a floating point number. So integers are like apples and floating point numbers are like oranges. We cannot multiply apples with oranges. So there's a problem. Because the representation for 2, the integer, the bit representation for 2 and the bit representation for 3.4, and the multiplication, the algorithm for multiplying integers and the algorithm for multiplying floating point numbers is different. Yes or no? At least forget about computers. When you want to multiply two integers, no, the algorithm that when you do manually, the way you do it versus the way you do multiply two decimal numbers is different, right? Algorithm. So the same things gets reflected in computer hardware also. Floating point multiplication is different from integer multiplication. So the computer has to use the appropriate multiplication operation in order to, it needs to know whether it is multiplying an integer with a integer or a floating point number with a floating point number. So it is easy to change. If you change pi to an integer, what happens? If you change pi to an integer so that we multiply integers to integers, then you lose that fractional part, which is not good. But on the flip side, if you change the integer 2 to a floating point number, is it all right to convert the integer 2 to a floating point number, to a fraction 2.0, right? So what happens is without there is what is called as typecasting happens. There is a typecasting operation, which this is automatically typecasting happens. So this float to this is what. So when float operator is applied to 2 gets promoted to 2.0, and you multiply 2.0 with 3.14 and you get 6.28. Remember the representation for 2.0 and 2, the floating point representation for 2.0 and the variable then on the integer 2, they are very different. Okay, are you with me in this picture? This is what is called as a typecasting. This is what is called as a typecasting, and this typecasting automatically happens. You don't need to do. But whenever you want to do typecasting explicitly, you can do something like this. You can put float to, you can do. What it does is this whole thing, it gets the result of applying this expression is 2 gets typecasted to 2.0. Are you all with me here? Yes, no? No issues, right? You understood the logic, why it's all from float to int will also be typecasting. Yes, Vaibhav. Any typecasting is from one type to another, it is typecasting. So, but here we don't need to use this. We just write 2 and automatically it gets typecasted. So 2 gets typecasted to 2.0, and anyway pi times radius, it's anyway it is no. So there is one interesting question from we can write 2.0 directly. That's a good idea also. You can as well write 2.0, no problem. Good question. Good idea. Okay. We will have a broader discussion on typecasting whenever there is an expression. So here, this is what happens. There is this nice question. So even if, yeah, so let's see, this is 2. So what happens is, yeah, this is promotion. So if you see 2 times pi, this is the place where we have seen 2 pi is a floating point number. In fact, it is a double. So it's a floating point number. So what happens is this 2, when you are multiplying an integer with a floating point number, then the integer gets promoted to float. Are you with me? Yeah, let's this much you keep in mind. We will revisit the ideas later. Okay. So now let's compile this program and see what are the important ideas that we have seen in this now. We looked at floating point numbers, we looked at left associativity, we looked at typecasting, a very good set of ideas we have seen. And let's compile this program and see how it works. Let me use slash. So even if you enter an integer, it will read it as a, since we use %f, it reads it as a floating point number, or we can use 3.2 for example. Yeah, if you use brackets, we break the left associativity. Okay, I hope you're all with me on this example. So what other? So few things. If you see when you are printing how many digits? You are printing 6 digits after the decimal point. And you may think, I don't want 6 digits, I just want 3 digits. Then maybe, you know, this particular thing that is you're saying person dot 3f, it will tell that I just want 3 digits after. No? So now only 3 digits are printed after the decimal point. So now you have seen one more nice idea that in terms of format specifiers, you can actually manipulate how many digits you would like to get printed on the screen, so on and so forth. So I don't think it will do the, yeah, so it doesn't do the rounding. I think it will just truncate the things. Lakshmipati Balaji, I think so, yeah. So I don't want to go more into formatting because there are tons of things that you can do with formatting. We will get digressed. But this much, this cool idea, you know, at least that you can control the number of decimals you would like to print, the number of digits you would like to print after the decimal point, you can control using dot 3. Okay. So now one of the goals for yeah, one topic which I would like to cover, it got covered. I would like to rename this program as circle.c, move float.c to circle.c. So now we want to find square root of a number. Okay, so let's try to find control. This you need this for one of the problems. Include controllers sqrt.c. So hash include stdio.h main scanf %f ampersand n sqrt n is equal to Chinmay, you should leave it. If you don't understand something, it's not coming your way for other things, right? So you need to learn what things to leave, and then you'll understand it later when we talk about functions. Okay, so don't worry about it. So it's important you kind of if something is not really coming in the way of understanding, we can leave it there. Just write this. Yeah. Percentage. Okay. Fashion. Thank you. So here, let's compile this program and see what happens. So GCC sqrt.c. Now you will see that sqrt, it's a library function. Printf is a library function. And in order to use printf, we have to include stdio.h. And in order to use square root, we have to include math.h. And in fact, if you go and check the man page for sqrt, you will get nice information, that in order to use it, we need to include math.h. And and then sqrt takes a double and then it returns a double. Okay. So what happens is, but we are using floating point numbers. Okay, is it going to be a problem? Float n sqrtn. It's not a problem because floating point n gets typecasted to a double n. I want you to remember n, which is a float, the representation for n, the floating point representation for n and double precision representation for the same. Let's say if the input is equal to 6 point, let's do this. Let's draw the same this thing. So we have sqrtn is equal to sqrt and then we have n. But sqrt expects a double precision number, but the n that we have, it's a floating point number. It doesn't work actually. There is a problem. But what the compiler does is it automatically typecasts n to a double. This is, so n, the value of n, it gets typecasted to a double, and it is, so in that process, do we lose any information? Do we lose any information while typecasting from float to double? So wherever there is no loss of information, since double is bigger, the compiler generously automatically does the typecasting. Okay. And when the return, when the SQRT, the return value, it again needs to be typecasted actually, because SQRTN, it is a floating point number. So the double value returned by SQRTN, it needs to be typecasted to float. It needs to be typecasted to float. So remember these things. So when we go from float to double, there will be some loss of information. That's true. There will be some loss of information. So now let's do, because yeah. So we need to be aware here. So when we are doing this thing, we need to be aware that the double number is being typecasted to a floating point number, and in that process there is a loss of information, and that loss of information could cause a bug in your program. Yes, if you go look at the man page for SQRT, SQRT all the time returns a double. It takes a double, it returns a double. And if you want to use the floating point version, then you have to use SQRTF. Are you with me? So what happens is, let's say if you are writing code for a rocket, you are writing a controller for a, which controls the trajectory of a rocket. Okay. And no, you are computing this square root, and what happens is there is a minor loss in information when the double number got typecasted to float. But what happens is this error, this minor error, which is negligible, because you keep repeating this computation as the trajectory keeps, as the rocket keeps going up, and these errors can accumulate and it can have a exponential effect. And rocket, instead of going up, it can go down and fall into sea. Okay. So when you are doing working, you have to be completely aware of what is happening, that hey, there is a loss of information, but I understand it's not an issue in this particular use case. And sometimes we have to prove this theoretically, just not like, yeah, it looks all right to me. I tried out a couple of examples. No, I'm not seeing anything wrong. It's not like that. Are you with me? Remember this, there is a loss of information, and such loss of information could lead to big problems, especially in some applications, a rocket crashing, you launch something to Mars, that there could be, the errors keep on accumulating for a period of 8 months or 9 months of journey. So instead of landing in one place, it may end up landing in a different place, where it will end up landing in water, for example, if there is water in Mars. Okay. So remember that. So you have to be, good question, Chinmay. So first of all, when you are losing information, you need to be sure that it is all right to lose information. In the particular, how do you ensure that it is all right to lose information? It's a very difficult question to answer. Very, very difficult question to answer. Okay, so now so GCC sqrt.c. So now it's still not compiling. See, what happens is, yes, the code, the instructions for the square root function are present in math library, and it is not automatically linked with your program. Whereas the code for printf, or code for scanf, they are automatically linked because they are standard library. So they are standard libraries, printf, scanf, but math is not a standard. The square root, which is part of math library, it's not automatically linked to your program. Okay, link, what is linking to your program? So the code for your libraries, there are different libraries. Okay, there is there is math library. Sorry. There is there is some standard input output library. Like that, there could be different libraries. And this is your program. This is your whatever my program. So what happens is when you are using SQRT function here, the instructions associated with SQRT function, they need to be pulled in into your executable, and so that your program can successfully execute. So for we are not explicitly linking the standard library which contains printf and scanf, because it is automatically linked. So whenever a new library is, you are using a library which is not by default linked, this process of pulling these instructions into your program is called as linking process. And hash include math, it doesn't tell you hash include math.h. It doesn't enable the linking. All it tells is, it tells us that SQRT is a, it's a double. Yeah, let me do, I'll explain. I'll take a pause here on the program and then explain to you one interesting idea, and then we will move on. So GCC, let's compile this, minus link math dot a dot out, square root of 4 is 2.0, square root of 4.3, 2.07, so on and so forth. So now let's take a look at the code. So I want to say printf sq, what do I say? Yeah, printf square root of 9. Let's see what happens. 9.2 is equal to %. If it's not complaining. Okay. See, what happens is, what is the problem part? Hey, there is a particular thread of thinking that we are going through now, and what is the problem? I will take that question later, but let's say if we are trying to understand some ideas, let's try to understand them, and then so those questions we can take during tutorial hours, or okay. So there is yeah. So here, when you include the math.h, the code for math.h is not included, but the signature for various functions knows what is the signature for a function, the type of the parameters that we pass. If you see the man page, what is the signature for the SQRT function? The signature for the SQRT function is this. It takes one parameter, its type is double, and returns a value whose type is double. This is the signature for the SQRT function. So this signature will be present in math.h, so that if you kind of, like, for example, instead of square root of n, let's say if you use a data type which is not which doesn't match the function signature, the compiler will generate a suitable warning or error saying, hey, you are not supposed to do this, but this is what you are doing. Okay, like for example, maybe the signature is not the program. The signature is not the program. So let's do one thing. Let's compile this program, CPP. Let me CPP sqrt.c greater than sqrt.i. Control O. So now this is all math.h code. Okay, so all these lines you will see. And then if you search in this code, sqrt, yeah. So you can see this looks a bit yeah, weird, but I think yeah. So I wanted to pay attention to line number 873. 873. Yeah. You can see. So this is the place where you can see this declaration. I want you to keep in mind, observe these three things in mind. First thing, pay attention, guys. The code for SQRT is not included. Only the signature for SQRT is included. The first, the parameter type is double. That's what it is saying. There's the SQRT takes one parameter, and the type of that parameter is double, and it returns a double. It returns a value. The type of the return value is double, and then there is this keyword called as extern, which means that the function SQRT is not defined as a part. It's not defined as a part of this code. It is defined elsewhere. That's what extern means. It is the code for SQRT is available external to this source code that you are working with. That's what it means. So when you do the include, this is the signatures of various potential functions which you can use. They will be included. Like for example, on line number 870, you can see the signature for power. PO is computing the power. How many parameters does POW has? How many parameters? 2. What are the types of the 2 parameters? Double and double. And what does it compute? It computes x power y. And what is the return type value? Double. Is the code for POW included when you include math.h? No. Where is the code for POW present? Somewhere else in the math library. In the math library. Okay. No, not in stdio.h, not in math.h. The code for POW or SQRT, it is not present in math.h. It just contains the signature. Okay, it is present in some external library. Okay, math library. Are you all with me? The signature for SQRT is part of math.h. Okay. Maybe if you go to CD, I don't exactly know where it will be. Find dot minus name star dot so. No, math.h doesn't give a reference to. Yeah. I'm just trying to find where stdlib.so. The signature is part of math.h, but the full code is not. S5O. Yeah. Exactly, Naneshwar. It's like math.h only contains how the function should take input and give output, whereas the actual instructions of the program are present somewhere else. And you know, all these files that you are seeing, you know, .so files, they contain code for different library functions. And I'm just trying to find what is the library for math. Can someone help me out? Does anyone know where math library resides? lib64. Okay, anyway, so it will be there somewhere. What do you mean by understand the logic of the underlying code? Part? Square root logic. So that's a problem which we will solve. How do you find square root from your +2? How do you find square root path? Okay, next class, the problem is how do you find square root? Okay, we'll solve that problem. Okay. There's an interesting technique using which we can find square root of a number, or you know, more interesting things. It's not exactly binary search, but we will use a interesting technique. Okay, are you all with me so far? Doing all right. So now I wanted to do this read, print, float done, square root and math library done. So now we will learn about arrays and for loops. Okay. Now let's say we want to write a program which computes the sum of first n numbers. Okay. So we can write what is called as a for loop. For loop makes a lot of things. You can just do it with while loop also, but for loop makes many things easy for you. Okay, but so let's first look at for loop from this book. Control structure. Yeah, you see, so the structure of for loop is this. Okay, it has for, this is the syntax of the for loop, for, and then you will see two parentheses, and then there are three parts to it, and the three parts are separated by two semicolons, and then there is a body of the for loop. And you can see for I is equal to 0, I less than 10, I plus plus statement. So if you look at this code, let's try to Control S, test for.c. Okay, hash include std page. Enter n. Okay. Yeah. N. So for I is equal to 1, I less than or equal to n plus plus I, printf. Void. Okay. Scanf %d ampersand n. I plus plus I, it just increments I. Thank you, guys. So you're all good. So plus I is you increment I, or you just write I is equal to I plus 1 for the time being. This is not a big deal. I is equal to I plus 1. You can do that. So if you look at this, the flowchart for statement, the flowchart equivalent for this for statement is I is equal to 1, and then you have this statement. So you check if I is less than or equal to n. So there are two possibilities. If yes, I is less than or equal to n. If I is less than or equal to n, then whatever that is present in the body of the for loop gets executed. Printf. In this particular case, we have only one printf statement. And after it gets executed, what happens is the statement I is equal to I plus 1 gets executed, and the control goes back here. You keep going like this. On the contrary, if you get no, then the statement which is after printf, which is after the body, in this particular case, we don't have anything in the body. Let's say I will have something like return statement. So this is what we have. Then what happens is whatever may be the statement that is after that body of the for loop, it gets executed. Does this make sense? Are you all with me? This code, if you look at this flow chart, so I is equal to 1, and then you keep looping through the thing. You execute the body, or you check the condition, and if the condition is true, you execute the body of the loop. And then after you execute the body of the loop, you do whatever the operation that is specified here. So if you use a different color code here, so this is 1, this is 2, this is 3, this is 1, this is 2, this is 3, and this is 4, this is 4, and this is 5, and this is 5. So now we are just saying return from the program. It can be any statement. Return from the main function. It can be any statement. If you don't put return also, it is fine. Return is implicit there. By default, it will be automatically be included. Do you understand this program structure? Okay. So now I will just make one modification to this program to compute the sum of first n numbers, and after that we will stop today's lecture. We will talk about arrays in on the Thursday class. Okay. So let's see. Yeah, I want to clear all my. Can I clear all my drawings? So now we want to compute the sum of first n numbers. So we take sum n is equal to, we can initialize a variable at the time of declaration itself. So we want to use the variable sum n to have an estimate of the sum of first n numbers. The initial estimate that we hold is 0. Are you fine with it? The initial estimate of the first of n numbers is 0. That is the initial estimate. And every time we iterate through this loop, what do? We improve our estimate. And how do we improve our estimate? We say sum n is equal to sum n plus I. So every time we go through this loop, our estimate keeps on improving. And by the time we finish off the loop, our estimate matches the exact value of the sum of first n numbers. What are we doing online? We start with an initial estimate of the sum of first n numbers. What is the initial estimate? 0. After the first iteration of the loop, what is the estimate? After the second iteration of the loop, what is the estimate? After the third iteration, 6. Right? So as we keep going, we keep improving our estimate, and finally we converge and we say, hey, this is the sum of first n numbers. And we just print here, printf sum of first percent n equal to percent d numbers is percent d n comma sum n. Okay, let's compile this program and see what happens. Okay, so what is the program name? This is test4.c. Okay. So if you say 5, sum of first 5 numbers is 15. We compile the program again. Sum of first 10 numbers is 55. Are you all with me here? Or you want me to use GDB and show you again what is going on? Okay. So now with this, so with the for loop, with the floating point, will you be able to do problem number 4? Problem number 4, it's very simple now. With this background, you should be able to do it. So problem number 1, problem number 2, problem number 4 are taken care of. What is problem number 3? Co-primes. Huh? Okay. And then the last problem is on dot product. No? That dot product problem, after Thursday class, you will be able to do in no, less than 5 minutes. I can assure you. Don't worry about it. So now that leaves you with the co-prime problem and then the challenge problem, the first challenge problem. The second challenge problem is easy only. The first challenge problem is only a little bit tricky. Yeah. So it's all right with them. Agarwal. C is case sensitive. Okay, so that's all I have for you today. You can use other methods to find square root and it's all fine. So that's all. Are you all good with today's lecture? We introduced a bunch of ideas, no issues. So yeah, please. And then on Thursday class, we will introduce arrays because we don't have time today. We'll do it slow and we solve a couple of problems and we should be good. Okay, so we'll stop the lecture here.